Welcome everyone to another live session for the online class and anyone else who might find this by other means. This is going to be one, we'll try and keep it going. I'm about to go on a 5-week trip to Italy to the Rockefeller Center in Bellagio and to do a project on distance education, democratization of higher education, and in fact MOOCs are part of that project. So I'll be on a Italian time zone, and we'll try and do Skype live sessions, a couple of them remote while I'm there during that 4 to 5 weeks. To keep this all rolling, but otherwise, glad to have you with us, and we will open the floor momentarily for questions on any topic in astronomy.
Excellent. Welcome, everyone. We are happy to have you with us today. We have a little bit of a different setup, so that's why we are late. I appreciate your patience. We're going to start with one of the questions from the live chat, and we will grab from the window. So post your questions in the chat, and we'll grab them from there. So the very first question is from Kendra Smith. Can the gravity of one galaxy pull or push on another galaxy?
So yes, galaxies exert gravity, and when galaxies are adjacent in space or near each other in space, they exert gravity, and really it's described simply by Newton's law. The galaxy acts as if it has its total mass concentrated in a point at the center, and you can simply use Newton's gravitational equation to calculate the gravitational force between them, even though the galaxy is a distributed object. When you're using the mass in calculating the gravity two galaxies exert on each other, of course, the bulk of the gravitational attraction, about 80%, is caused by dark matter, not by the visible material. So it's very important to have a census of dark matter, otherwise that force will be calculated wrong. And in fact, inverting the logic, we use the way galaxies move and the implication of that force to infer the dark matter in galaxies. That's really the main reason that dark matter is inferred to exist, going back almost half a century now.
I'm still dealing with the sound, so can you maybe just do a quick recap of that, because some of it got cut off.
The whole, should I just read the whole thing?
Yeah, I think that's probably the best idea.
Do I have to wait again?
Nope, we are set to go now.
Okay. So two galaxies do exert a force on each other, and it's really described by Newton's law of gravity. You don't need general relativity to talk about the galaxy force one on another. The galaxies act as if all their mass was concentrated at the center of the galaxy. And of course, the important point is that you have to count the dark matter, which is 80% of the mass and therefore 80% of the force. Now in astronomy, we've inverted this logic and used the way galaxies move, responding to the gravity they exert on each other, to infer the presence of dark matter in galaxies.
Excellent. All right, we are all set up now. The next question is going to be from another one of our live participants. Let's see, we'll go to Mega Gadad. What is there or was there before the Big Bang?
We don't know. The Big Bang theory or model does not describe what caused the Big Bang or the precursor state. So the basic simple answer is we don't know. No idea, actually. It is a matter of pure speculation in cosmology what there was before the Big Bang. In truth, there doesn't have to have been anything before the Big Bang, because the Big Bang theory, going back to quantum genesis, implies that the universe, all the mass and energy in the universe and its expanding state, could have emerged from the vacuum, from total vacuum. And so you don't actually have to have something before the universe started.
The next question is from Hani Hamza, who would like to know if you can talk about the Drake equation and sort of solving the Drake equation, if that's even really a thing.
The Drake equation is an iconic formulation of SETI, the Search for Extraterrestrial Intelligence. The story of the Drake equation is, of course, Frank Drake was a young researcher, a postdoc, in 1959 when he went to the National Radio Observatory, and there was a meeting organized on the search for extraterrestrial intelligence. It was the first ever meeting on that subject. There were only a dozen attendees, pretty much all the who's who of astronomy at the time. Frank Drake, for example, a chemist who won a Nobel Prize during the meeting, and various other iconic figures in astrobiology. And Drake went to the blackboard at this meeting, and really without an agenda, he in pretty real time wrote the Drake equation on the board as a way of combining factors to calculate the number of intelligent communicable civilizations in our galaxy that you might communicate with or hear messages from in the act of SETI. And so that's how long ago it was, 60 years ago. We still use the Drake equation. Even Drake was modest enough to say that the Drake equation is a container for ignorance rather than a way of solving something, an equation that we think of normally solving something and getting a number at the end. There is no answer from the Drake equation because the first three factors are astronomical, and in fact we've measured them, which is the number of Earth-like planets around any star in the galaxy, the rate at which those new stars are forming, and the likelihood that those planets are habitable. We now have information on that. But the subsequent factors, the probability that life emerges on a habitable planet, the probability that it becomes intelligent, the probability that it develops technology, and the duration of that civilization, completely unknown. So when you have an equation where you have factors you know, multiplied by factors you don't know, the answer is you don't know. So unfortunately, that's the simple truth of the Drake equation, and it's been true for the whole time. So we will have to make progress in the search for life in the universe, microbial life, which we are making progress, before the Drake equation will get crisper and allow us to maybe say something about how many civilizations are out there.
Excellent. The next question is from, again, one of our live participants. Can you explain, from Pramod Argadi, who asks, would you please explain why the inner planets are rocky while the outer ones are gaseous?
So there's a standard theory of solar system formation, our solar system and others, which holds that the rocky planets form interior, close to the star, and the gas giants form further out. Now the important point is that all four gas giants in our solar system, Jupiter, Saturn, Uranus, and Neptune, do have rocky cores. Those rocky cores are inferred to be 3 to 10 times Earth mass. So really you can think that all the planets are rocky planets at their heart. The only thing is that the outer planets have an additional envelope of gas, which in the gas giant's case is most massive, is more massive than the rocky core. And so we think that in the inner solar system, the pressure of radiation from the young sun drove away the gas, and there wasn't that much gas in those inner orbits anyway. And so the things that formed were just rocky aggregations of the rubble material that was in the protostellar disk. In the outer solar system, the rocky cores were the same, and over time they attracted gaseous mantles, or gaseous atmospheres, because there was a lot more gas out there and the gas was cooler, and so they gradually, although it only took 10 or 15 million years, grew into gas giants. Now that's the conventional story. It's been complicated by the fact that we know that planets migrate, but that's the basic reason there are two types of planets.
Excellent. The next question is, again, from one of our live participants who would like to know, let's see here. Alexa Olison asks, a question about the JWST and telescopes in general. Do they gather data only and then the data is used to generate the images? What data is actually gathered from a telescope, and how much of the astroimaging process is guesswork?
Typical story with it's either a ground-based or a space-based telescope, it's the same, is that these telescopes have imaging devices. They have electronic two-dimensional detectors, arrays of electronic detectors. These are called CCDs when they work at optical wavelengths, and they have various names, based on the materials they're made out of, working in the infrared, where James Webb works. But you can think of them as infrared CCDs. So these telescopes have CCDs, and at the telescope, the light comes in and basically converts into electrons, and those electrons are read out from each of the pixels into a digital signal, which is then stored in an onboard computer. And that's true whether the onboard computer is up in space with the James Webb or adjacent to the telescope on a ground-based telescope. And only then, when that electronic data can be manipulated, do you end up getting an image. So the telescope itself does not make images. It sends a stream of electrical signals which represent the readout of how many electrons have been collected, converted from photons, from the light that hits the two-dimensional detector. And that's the way most astronomy instruments work. The creation of an image happens downstream in processing.
The next question is from Nerd Uno, who would like to know, what is your opinion of your peer, Dr. Avi Loeb, claiming that the Oumuamua object spotted in 2017 is of artificial origin?
So Avi Loeb, who I know fairly well, he's a senior figure in astronomy. He was the chair of the astronomy department at Harvard for a decade, actually. And he's a very well-known cosmologist, an excellent cosmologist. He's started to dabble in fields more farther flung than cosmology, much closer. And yes, he got very intrigued in Oumuamua and decided that its orbit and its physical shape and properties were so unusual that he presumed it would be better explained as an artifact, an alien artifact, than a natural body. And he got into this enough to write a couple of academic papers and then an entire book on this. And he's been doing the circuits of the news stories and been on TV and been interviewed many times. And so he's heavily promoted this idea. The truth is that the conventional wisdom in the planetary science community is you do not need that explanation for Oumuamua. There are ways you can produce highly elongated and fairly reflective interloper objects that could then travel into our solar system with the velocity and trajectory that this object has. It's unusual, but it's not unprecedented or inexplicable in terms of solar system objects. So the conventional story is that you don't need to reach for the alien artifact explanation. Loeb has, of course, himself kind of amusingly inverted Carl Sagan's argument that extraordinary claims require extraordinary evidence, which would normally be used to refute his hypothesis. And he said that extraordinary situations require you to let go of your conservatism, require extraordinarily bold thinking, and he just claims to be a bold thinker. There's a fair amount of ego going on here, as you can probably tell if you've read some of the articles and the interviews. So the conventional wisdom may be right, and it's possible that Loeb may be right. I mean, the door is not completely closed on what this object is.
The next question is from Kamertani, who says, hello, Professor Impey, thank you and your team for the astrobiology course. What do you personally think of the simulation hypothesis? Like, could our universe be a super complex, enormous simulation?
I view this simulation hypothesis as a provocative argument pretty much from philosophy rather than from physics or from science per se. It's an argument of extreme skepticism to say that the physical reality that we presume to be the universe we live in is all created as a simulation. Essentially, we live in a computer simulation and we're just not aware that we do so. It's a radical hypothesis, and you can take it seriously if you want, but you'd have to ask, well, what is the real evidence for this? And the truth is there is no direct evidence for it. It's just a hypothesis, a radical hypothesis that turns out to be fairly hard to refute, because of course if it's a perfect simulation, these are intelligent aliens far more intelligent than we are, they're not going to make buggy software, they're going to have a simulation with no glitches in the matrix. So you could just argue that there's no way we'd be aware we live in a simulation. And that's a sort of circular argument in a sense, which is why some people do not find the simulation argument particularly convincing.
The next question is from one of our live participants. David Wismer would like to know, if dark matter is a subatomic particle whose wave function doesn't collapse, would this explain how it imparts gravity and is also hard to detect?
I don't think you need to go to the idea that the particle is something whose wave function does not collapse. There are many particles in the standard model of particle physics where a collapse of the wave function is not a problem or a concern. I think the best hypothesis for the dark matter subatomic particle comes from supersymmetric theories that sort of go beyond the standard model of particle physics and hypothesize a shadow set of particles that are mirror particles, and this sort of unites the fermions and the bosons, the spin, integer spin and half integer spin particles. And the heaviest, this most stable, lightest stable supersymmetric twin turns out to have about the right properties to be the dark matter in the universe. And so that is still a viable hypothesis, but lab experiments are actually narrowing the real estate where the dark matter particle could possibly live in terms of energy or mass. And so it's not clear this hypothesis will stand the test of time.
The next question is from Say Montreal, who asks, have you heard about the idea that tiny black holes or a tiny black hole might replace neutrons in an atom?
The idea of tiny black holes is a conventional idea in physics because black holes in principle can form of any mass. I'm not familiar with that particular idea that tiny black holes could replace subatomic particles, but of course it is in principle possible to have a black hole that's the mass of a neutron or a proton. There's just no evidence they exist, and if Stephen Hawking is correct, then the evaporation time of a tiny black hole would be in an infinitesimal tiny fraction of a second, and these black holes would essentially evaporate. They'd fizz away in no time at all. So therefore it's very hard to imagine these kind of tiny black holes existing in any stable form of matter.
The next question is from Pramod Argad, who asks, would you please explain the role played by the conservation of angular momentum in accretion?
Sure. So accretion is a fundamental physical process that occurs in quite a large set of regimes in astronomy. It occurs essentially anytime you have an object with an environment where it can pull in matter by gravity. Accretion can in principle be spherical, so it's possible for accretion to occur by a spherical flow onto a star, say. But generally stars tend to have angular momentum, and so the angular momentum means you end up usually with a disk, and so people talk about accretion disks. And they're governed by two forces. They're governed by the conservation of energy law and the law of angular momentum, of conservation of angular momentum. So as material moves through the disk towards the innermost radii, it must conserve angular momentum and it must conserve energy. And so these are boundary conditions, or rules if you like, that govern the behavior of accretion disks.
The next question is from Horst Melcher, who asks, astrophysics has made most dramatic advances in, say, the last 50 years. Is this the result of smarter scientists like yourself, more advanced technology, or something else? To what do you give the credit?
I think the advances of astrophysics in the last half century in particular have largely been driven by technology and by innovations in telescopes and what we learn about the universe through observation. Astronomy is an observational science. Very few of the things in the universe were predicted. They've tended to be discovered. And so, driven by observation, the last 50 years has corresponded to the creation of a large suite of new telescopes. It's corresponded to opening up the electromagnetic spectrum with X-ray and infrared telescopes and detectors and gamma ray telescopes. Radio astronomy existed, going back to the 1930s. So this technological innovation, I think, is largely behind the progress in astronomy. The more foundational theoretical ideas actually go back some fair amount of time. The theory of star formation is almost 100 years old. General relativity is over 100 years old. So we haven't had any profound new theories, and the Big Bang theory even goes back to the 1940s. So I think the longevity and age of these basic theories of astronomy suggest that the innovation and the progress has been driven by observation and by technology.
The next question is from ASZ, who's on with us live. Do you know what will happen to the Arecibo Observatory? Do you think it will ever be fixed?
It's an open question. Of course, most people realize that even before Arecibo had its disaster, where one of the towers collapsed, the cables ripped apart, and the central suspended receiver platform crashed into the dish, essentially destroying it. Even before that, the Arecibo 305-meter radio dish had been eclipsed by the FAST, that's the acronym, the Fast Radio Telescope in China, which is bigger. The question of what happens to Arecibo is still up for grabs. Arecibo was already in financial trouble well before it collapsed, and in fact, many people have argued that the reason it collapsed was because of deferred maintenance, because the funding of the telescope was so difficult. The National Science Foundation essentially pulled the plug on a significant part of the funding. Cornell University, that had operated it for half a century, handed it off to another consortium. And so it was sort of orphaned as a facility well before the disaster. And those issues still remain. So if anyone's going to rebuild Arecibo, and there are definitely proposals out there, several proposals have been written, they're going to need federal funding. They can't really be done just by universities working together, because it's going to be too expensive. And given the difficulty of federally funding Arecibo before it collapsed, I'm not totally confident they'll be able to rebuild it.
The next question is from Mega Gadad, who asks, is our universe single, or are other universes out there? What about parallel universes? Is this a totally fictional concept?
So parallel universes, or as it's often called the multiverse theory, is a hypothetical, speculative theory in cosmology. It's not completely ridiculous. It's pretty out there, and there is no observational evidence to support it. So the idea of parallel universes essentially comes from the idea that our space-time, the totality of the space-time we can see with our large telescopes, is not all there is to physical existence. And the reason that this might arise is from quantum genesis, is from the Big Bang originating as a bubble of space-time in a quantum fluctuation from some precursor state, and the idea that there may have been other quantum fluctuations or other origination events around that time, or before or afterwards, maybe continuing forever. There's no evidence for this happening, and almost by definition, a space-time that's distinct from ours would not necessarily intersect with our space-time. So how would we be aware of its existence? So one of the big issues is that proving or disproving the multiverse or parallel universe idea is extremely difficult.
The next question is from Crawley Enterprises, who asks, Carl Sagan said we are made of star stuff. Can you explain what that means?
Sagan was alluding to the fact that the atoms in our bodies, all the atoms in the universe, more or less, except hydrogen, helium, and a smattering of very light elements, were forged in stars by a fusion process and then ejected out into space, where they could become part of planets and eventually people. So every single carbon, nitrogen, and oxygen atom in your body, and those are the three core chemical elements involved in life, every one of those atoms was once part of another star, was created in another star, because the universe at its origin was very simple and consisted just of particles and hydrogen and a little helium made in the Big Bang. So we are indeed literally and metaphorically star stuff, and that material predates the formation, of course, of the Earth and the Sun, because those atoms had to be incorporated into the solar nebula and eventually into the Earth and our bodies. So the age of those atoms and when they were created could be any time between 4.5 billion years ago, going all the way back to close to the Big Bang when the first stars formed.
The next question is from one of our live participants, is there an equation for the strong force like there is for gravity or the electric force?
Yes, there's a whole set of equations for describing the fundamental forces of nature. The strong force, that is the force that binds an atomic nucleus, is described by a theory called quantum chromodynamics. And quantum chromodynamics is a quantum theory that describes how the color charge, which is the charge that's exchanged between the quarks in an atomic nucleus, the quarks themselves being bound into protons and neutrons, how those operate. So quantum chromodynamics is a fairly complex theory. In physics terms, it's the gauge theory, and it's a fairly mature theory that's been around for 30 or 40 years now.
The next question is from Salma Essagar, who asks, we're living on the surface of the Earth, so what is inside our planet? And I'll add in, how do we know?
We have to use indirect methods. The deepest hole we've dug in the ground anywhere, the deepest mine, the deepest shaft, is maybe 10, 15 kilometers down. I don't know the exact number, but that's a pinprick in the surface. That's about as far into the surface as the thickness of the skin of an apple on an apple. So we've not directly probed very far inside our planet. Therefore, all the information we have about it is indirect. Essentially, we can use surface measurements, gravitometers and magnetometers, to infer the properties of the Earth below the surface of our feet, under our feet. But the most profound information has come from pressure or seismic waves. So we can we can essentially percussively hit the crust of the Earth in different places and then watch how the pressure waves propagate through the entire Earth, because these magnetometers, these sort of pressure gauges, are so sensitive they can detect on the far side of the planet when there was a disturbance. Now, these pressure waves happen naturally during earthquakes as well, and we can measure those. And the way those waves travel through the Earth and refract and bend, and the time they take to propagate, tells us about the density of the Earth, and we've got a very good density profile of the Earth as a result of these measurements, obtained over decades. It's quite a mature science.
The next question is from Robert Baker. Can you comment on the helical jet of the Blazar, and there's a number J19242914, seen by the Event Horizon Telescope before it viewed Sagittarius A star?
Yes, this has been published recently. A blazar, incidentally, is an active galaxy. It's a relative of a quasar. I used to work on blazars quite a while early in my career. Blazars represent a form of active galaxy like a quasar, where our line of sight looks almost directly down a relativistic jet onto the supermassive black hole that powers the object. In this case, the Event Horizon Telescope, with its exquisite resolution, I think the angular resolution of the images of this blazar are about 50 microarc seconds. So that's an incredibly small resolution, hundreds of times better than, say, an image from the Hubble Space Telescope. So it's a distant object, and you need that resolution. You can also measure the polarization, which allows you to infer the magnetic field. So the helical jet in this object, which is pointing almost straight at us, is constrained by magnetic field, and magnetic field is indicated by the polarization of the radio waves that the Event Horizon Telescope detected. So the Event Horizon Telescope has made a beautiful little map of this distant blazar and shown the helical magnetic field structure of this relativistic jet. The jet itself has been created or powered by the supermassive black hole at the center of this blazar.
The next question is from another one of our live participants. Hinzamrech, I believe is how you say the name. How does developing microlife help in astrobiology?
I'm not quite sure what the reference is to microlife. Miniaturized version. Is there any explanation of what he means by that?
There's not, but I'm guessing they mean like some very simple organisms, like artificial organisms.
Right. So astrobiology is mostly an empirical subject, which means we have to find life elsewhere in the universe before we can really talk much about life in the universe. But in the meantime, we do have some tools.
We have theoretical biology, which is the theoretical idea of how biology might operate in different circumstances. And we have tools that allow us to create and manipulate the toolkit of life, including artificial biology and organisms that have been created, sometimes even with different genetic codes. So in this sense, microlife, or understanding and even manipulating or inventing from scratch miniature organisms, including some that don't occur naturally on Earth, is going to inform us about what nature might have provided in different physical environments. It's a kind of young field. There are not that many people who do research on it. And it's going to help astrobiology understand how unusual life might be out in the universe.
Excellent. The next question is from one of our live participants. Camertani asks, what jobs, if there are any, can be related to astrobiology or astronomy if your background is computer science or programming?
Computer science and programming are really part of the core of what most astrophysicists do. Even if you're not working on computer simulations as your primary research, you're almost always writing computer programs of various kinds, perhaps to manipulate and reduce data, perhaps to model it and understand it. So computer programming is a really core skill. Now, if you have serious computer programming skills and you're interested in astronomy, of course there are many fields of astronomy that depend on computer programming and simulation. Astrobiology perhaps not so much, because astrobiology is an interdisciplinary field where the core disciplines are biology, chemistry, and planetary geology, and programming skills are not as obviously applicable to astrobiology.
The next question is from Frederick Fernandez, who asks, are there any experiments planned to test the cosmological multiverse? And then I'll go one further. Are there any that are possible?
The only idea I've heard that has any possible traction on testing the multiverse idea is the fact that if these distinct space-times exist, they may, at the point where they were generated, alongside our space-time, they may have imprinted themselves through gravitational waves. So the idea is there might be gravitational waves or gravitational radiation that exist in our universe that have been imprinted from an adjacent universe or space-time. So that's a potential mechanism, but the truth is the predictive power of the multiverse idea, is not good enough to say exactly what gravitational wave signature we should look for.
The next question is from Godfather48. What are your thoughts on us going back to the moon after so many years?
Well, NASA's ramping up its plans. The Artemis project is NASA's crewed vehicle designed to get us to the moon. The current plans calls for by the end of 2024. I suspect that will slip to 2025 or maybe later. But NASA does have a fairly ambitious plan to go back to the moon, and as we know, the private space sector is also planning that. Going back to the moon makes sense if we are serious about exploring the solar system in more detail. It's because the moon is obviously the closest place to go. Its gravity is fairly weak, so once you establish a base there and an operation, it's much cheaper to leave the moon and then explore elsewhere, like Mars or outer solar system, than it is from the Earth with its stronger gravity. The moon is also a place where you can practice and develop the technologies you would need to visit other places. You can get rocket fuel, you can get water from the lunar soil, you can separate that water into oxygen and hydrogen and therefore make oxygen to breathe and hydrogen as part of rocket fuel. So you have all the raw materials on the moon to support a sort of infrastructure for future space exploration. So as a stepping stone, it's a very valuable place to go. Obviously, when we went to the moon in the late 60s, early 70s, it was part of a superpower competition with Russia, and it was just a series of moon landings and some geological experiments, and that's a bit about it. There was no idea beyond that. If we go back to the moon, it'll be much more serious. It will be with the clear goal of developing a long-term human habitation.
The next question is from one of our live participants, Salma would like to know, when do you think humans will be able to travel to Mars?
I think it's within 10 years that we'll be able to go to Mars. Elon Musk has the most aggressive plans. He has his large rocket, his Starship, which was designed explicitly to go to Mars. I mean, it will be able to go to the moon and other places, but it was designed primarily to fuel the idea of building a Martian base. His timeline is less than 10 years, maybe 6 or 7, but he needs an awful lot of funding. His SpaceX is not generating sufficient revenue to support the development of the Starship and the building of enough Starships to generate a Mars colony. So he needs a new economic model if he's going to really go to Mars on that time scale. NASA will also probably go to Mars. First is sample return, but even the sample return robotically is not until the end of this decade. So realistically, the NASA's not going to go to Mars with humans for another 15 years. So this is a very difficult project, and I think some people are over-optimistic with their timelines.
Two of the folks on with us today, Gokul and Salma, both are interested in your thoughts about aliens. Do you believe in aliens? What about sort of their level of technological advancement?
I think as a statistical statement, it's fairly likely that intelligent aliens exist. Just the existential statement. Do they exist in the galaxy? I think the answer is probably yes. And of course, if they exist in our galaxy, there's a few hundred billion galaxies, and they should exist elsewhere. So the odds that we're alone in the universe as an intelligent civilization are very low, I think. As for the nature of such aliens, hypothetical aliens, there's really no way to gauge, because the history of life on Earth involved so many twists and turns, so much contingency, so many changing environmental situations and interruptions from impacts and catastrophes and mass extinctions, that there's no simple linear path between microbes and us and beyond us. However, it's also a fair statement to suggest that since we have only just in the very recent past developed technology and the ability to travel in space and communicate through space, that it's likely that any other civilization elsewhere that's done it has been able to do it for a lot longer than we have. That's a timing argument, and it's a statistical argument, but it's a fairly good one. So the odds that we're the most advanced civilization in the galaxy or beyond are also very low. But that doesn't actually help you decide what those civilizations might be like in any way. We simply don't know.
The next question is from one of our live participants. Since our universe is still expanding, would it be better to be able to travel at our current speed 2,000 years ago or 20,000 years ago? Or is the difference in size of the universe so small that, being able to travel now or 20,000 years ago wouldn't really make much of a difference?
So that's a good question, and you need a sort of sense of perspective on the expanding universe to realize what the situation is. So the Hubble constant, or the Hubble parameter, measures the expansion rate of the universe, and the local number for that is about 70 kilometers per second per megaparsec, which means every 3 million light years away you go, things are moving 70 kilometers per second faster. The distances, however, between galaxies are millions of light years. So if you work out in a human lifetime or civilization time of 10, 20,000 years, how far galaxies have moved apart, how much their expansion of the universe has carried them away from each other. So you take that speed, 70 kilometers per second, and multiply it by the number of seconds in a century or 10,000 years. It's a big number. It's a big number of kilometers, but in terms of light years, it's a small number. It's a small fraction of the distance between galaxies. So the basic answer is no, that on human civilization timescales, the expansion of the universe is imperceptible. It's such a tiny fraction on those small timescales over those large distances.
Alexa Olson would like to know, what have been the most surprising or exciting revelations from the Voyager missions since they left our solar system?
So the two Voyagers were launched in the 1970s, late 1970s, and they're the first objects to leave the solar system. We've now had 5 spacecraft leave the solar system: the Voyagers, the Pioneers, and the New Horizons spacecraft more recently. The Voyagers have shown us very interesting information about what's called the heliopause. The heliopause is the place outside the solar system, so well past the orbit of the outer planets, where the radiation from the sun meets the interstellar medium, and there's sort of a mild shock wave or a discontinuity, and that's called the heliopause. So that's really the boundary of interstellar space, and when the Voyagers reached it, it did not have the properties that most astronomers expected. The plasma physics of that boundary is quite complicated. So that was probably the biggest surprise from the Voyagers.
The next question is, why are all the planets revolving? If it is due to the force of the orbited body, so for example the sun, how is this force generated?
So all of it comes down to the initial conditions of the solar system. So if we rewind to the formation of the solar system, the sun and all the planets, we started with a large quasi-spherical or almost spherical cloud of gas and dust that had a small amount of rotation. So it was not a stationary spherical cloud, but it was rotating slightly, had angular momentum. And then as that cloud collapsed by gravity, the angular momentum it had meant that it collapsed preferentially along the pole of the rotation axis, and so you end up with a disk of gas and dust. And within that disk of gas and dust, there's angular momentum. It's the whole angular momentum of the disk has a vector with a particular orientation, and that means that any nucleations that happen within that disk, such as the formation of planets, they will share that angular momentum vector, and that means you expect the planets to spin in the same sense that they move around the sun, and that, with one exception, Venus, is the case. So the formation scenario pretty neatly explains how the planets should share the properties of angular momentum of the cloud that they formed from.
Our next question is from Faisal. Does the discovery of active galaxies and quasars at a distance of billions of light years mean that the early universe was more active and dynamic than today, and that the universe is changing?
Yes, it does. And in fact, we've been able to tell the story of quasars and active galaxies. These are supermassive black holes that we believe exist at the center of every galaxy, but they're not always active. They're not always accreting material and shining brightly, which is what makes them a quasar. And surveys over the last decade or so have told us the life cycle or the life story of quasars. And it is the case that the universe was more active in the past. So when the universe was denser, and hotter, galaxies were closer together, it was easier for them to exchange material for fuel to go to the center of galaxies, and there was a lot of gas available to fuel quasar activity. And so the quasar epoch, the sort of the peak of quasar activity, was a time at a redshift of about 2, which is a time about a third of the age of the universe. And subsequently, the quasar era has declined. The height of the quasar activity has declined because subsequently galaxies just move further and further away from each other, so interactions and mergers decline, fueling of the nucleus of the black hole at the center of galaxies declines, and the quasars are essentially starved. And so we expect to see a lot of sort of massive dead black holes in galaxies around us in this local universe, and we do. And relative to the peak of the quasar activity, the space density or the sort of density of nuclear activity of active quasars here and now is 100 times less than it was at the peak of the quasar era.
Robert Baker would like to know, could a small radio telescope at L2 or in space or anywhere greatly increase the resolution of the Event Horizon telescope?
Yes, it's a good point. I mean, the resolution of the Event Horizon Telescope is determined by the baseline between the various dishes, because you combine the signals from the separate dishes to produce a resolution as if the entire array had the size of that separation. And at the current Event Horizon Telescope pretty much spans the Earth, so the resolution is given by the diameter of the Earth. If you wanted to do better, you could put a telescope in orbit, but low Earth orbit or even a high Earth orbit doesn't actually extend the baseline very much. So to do substantially better, yeah, you would have to liberate the radio telescope from the Earth's gravity and send it to some more distant location. The trouble with sending it to L2, or one of those far off Lagrange points, is that coordinating the spacecraft and combining the signal coherently from a very remote radio telescope to a terrestrial array has never been done. And the technology to do that is essentially unproven. So while yes, in principle you could get incredible resolution by putting one or more dishes far away from the Earth to be part of the Event Horizon Telescope array, the practicality of doing that has not been solved at all. And there's no plan to do it actually at the moment.
The next question for today is Nita Frank asks, how are we so certain that what created the riverbeds on Mars was water and not some other liquid?
Well, it's a good question, because we're inferring something that happened a long time ago, possibly even billions of years ago. Mars is not geologically active, so once it loses its liquid water or the ability to erode, then the surface features should sustain. So partly it's simulation and lab experiments. So you can, for example, in a lab, you can show that a channel or a gully or a geological feature could not have been carved by moving particles like a dust storm or rocks or sand just moving down a hillside. So it's fairly easy to show that a geological feature on Mars must have been carved out by a liquid as opposed to solid particles of some kind. To show that it's water, you can't really do that directly, but water is the most abundant liquid on Mars and inside Mars. Hypothetically, there are other possible liquids like ammonia and so on. They exist. I mean, they're in trace concentrations on Mars, but there's so much less of any other liquid than water that water maintains its status as the most viable explanation.
The next question is from Dan Cooper. Have you read Lawrence Krauss's book, The Physics of Climate Change? And if so, do you have any thoughts on it?
I'm going to have to pass on this one, so I haven't read it. I know Lawrence Krauss, he's a well-known cosmologist. I didn't actually know he'd written a book about climate change, so I will check it out.
Excellent. The next question is from Mega Gadad, who asks, can you talk about the M13 cluster? I've heard that there are potentially many Earth-sized planets. Is it possible that there could be aliens there, or frankly, any close cluster to us?
So clusters are interesting environments for looking for planets. They give you the benefit of being able to target a large number of stars in one exposure. So if you're looking for transits or eclipses, for example, looking at a cluster makes a lot of sense, because you can harvest the eclipses statistically from a large number of stars. On the other hand, if the cluster is a dense cluster, M13 is not a particularly dense cluster, but if it is a dense cluster, then stellar interactions could actually disturb planet orbits and toss planets out of the system. So it's not sure you could get stable, long-lived Earth-like planets on Earth-like orbits in a system that's dense in a star cluster. At the moment, there's a lot of unknown information about M13, so we don't really know how many Earth-like planets there are or whether they're habitable. So the information on the planets in M13 is pretty rudimentary.
Nita Frank would like to know, how long can humans remain on Mars before they would suffer irreparable damage and might no longer be able to return to Earth because of bone density or other problems?
So it's a good question. I mean, Mars is a hazardous environment. It has the magnetic field is so weak that radiation pounds into Mars. The atmosphere is thin, and so there's really no shielding and protection. All the plans for Mars habitation either assume that the habitat would be underground, perhaps in a naturally forming lava tube, or that you'd build a dome and then cover it with sort of slump block layers of it. So probably maybe even a meter thick of Martian regolith turned into building material, and that would be pretty good shielding. So, the plans essentially call for shielding the inhabitants of Mars, and if they went out in rovers and explored the terrain, not do it for very long. Definitely they're increasing their lifetime hazard of radiation. To get to Mars in the first place for an 8 or 9 month trip, they would experience several times a typical lifetime radiation dose of a human on Earth. I mean, that's not fatal necessarily. It increases cancer risk by some marginal amount. But if they were not in a very sheltered environment, then I doubt that Martian colonists could survive more than a year or two without having extremely high rates of mutations and cancers and life-threatening problems.
Yashwanth Shiva asks, the universe is so vast and the possibility of aliens is so high, so why haven't they reached us yet?
That's a good question, and of course it's Fermi's question. Fermi in 1950, Enrico Fermi, the famous physicist, asked hypothetically, where are they? He knew the logic of the vast universe and the materials for life being widespread and the amount of time there had been for evolution of complexity and intelligence and civilizations, and he said, well, they should be out there, so where are they? Why haven't they visited? But even if they exist, there's plenty of reasons why they might not have visited. Space could be so large and the number of civilizations low enough that the travel times are, crazy, that they're just long and they haven't happened. Space travel could be a cultural thing. It's possible there could be intelligent civilizations with very impressive technology that just choose not to travel in space or explore space. It may be just something we've chosen to do, but others do not choose to do. I guess it's also possible that they're so advanced we wouldn't actually recognize them, even if they were here. That's an interesting hypothesis.
The next question is from Leota Quigley Burns. Has NASA looked into searching more for life on other planets? If so, what impact will that have on people's religious views?
NASA's putting a lot of its eggs in the basket of Mars, so NASA, really has tried hard to look for life on Mars. They're going to bring back samples in 5, 6, 7 years and look for ancient fossilized life forms, and has more primitive plans to go to the outer solar system and look at Europa, Enceladus, and Titan as possible places where there's life. NASA, as a scientific agency, tends to steer away from any larger discussion of the implications of finding life on Earth for religious views or our self-image or our place in the universe. They just tend to stick to the science itself, which is probably a safer thing to do.
The next question is from Berhane, who asks, can we create an atmosphere on the moon?
Not really. The odds of creating an atmosphere are very low. The gravity is 1/6 that of the Earth, and so if you put a material that the Earth's atmosphere is made of, the average velocity of those molecules would be high enough to be above escape velocity. So you almost as soon as you made an atmosphere, it would be leaking off into space, and there's really nothing you can do about that. That's just gravity speaking there. So that's the fundamental reason why creating a lunar atmosphere is implausible. The calculation is different when you get to Mars, which has about 40% of the gravity of the Earth. There, you could plausibly thicken the atmosphere through technology, and there are people who've talked about doing that.
The next question is from Pramod, who asks, it is generally said that using a Hohmann orbit, it would take 6 to 9 months to go from Earth to Mars. Would we use the same kind of Hohmann orbit to come from Mars to Earth? And if so, how long would that take?
Yes, these orbits are the calculations are very similar, and the travel time is quite similar. It's actually slightly shorter. Depends on the alignment of the planets, of course, when you want to do it, how long they would be there. Because if you get them there on a particular home in orbit, then you have to worry about how long they'll be there before you bring them back, and you may have to wait until the planetary alignment is good, and that could be a year or 2 years. In principle, you use a little less energy getting back to the Earth because you're moving towards the Sun, but that turns out to be quite a small effect. Well, it's happening all around us, and I think the future of space involves a large component of the private sector and commercial spaceflight. Last year was the first year, 2021 was the first year in the history of the space program since Sputnik that there were more commercial launches to Earth orbit than government launches to Earth orbit. So it's a very dramatic situation for the first time in the whole history since Sputnik. Now that's a clear sign that commercial space aviation is here to stay. The price per kilo of launching to Earth orbit has gone down by a factor of 10 in the last decade, mostly due to the work of Elon Musk and Jeff Bezos and the technologies of SpaceX and Blue Origin. So that economy of reusable rockets means that the economics of getting to Earth orbit have transformed, and I think these are the reasons why the commercial space activity is here to stay and should grow quite dramatically. What's missing, of course, is a revenue stream. Musk and Bezos are funding their activity, each of them, by investing roughly $1 billion of their own personal fortunes every year. And that's, even for rich people, that as rich as them, that's unsustainable in the long term. So there will need to be a revenue stream if this activity is truly going to take off.
And the next question, and this will be our final question for today, is from Claire Nyquist. Can you talk a little bit about the Focal project and the potential for using the Sun as a gravitational lens?
Yes, this is a very ambitious, visionary project proposed by NASA to use the Sun as a telescope, basically. So use the gravity of the Sun as a telescope. If you choose the correct position to put your detector, there is a very distant point behind the Sun where you can form a focal plane, so a focal pair, if you like, an object and an image, and therefore achieve the magnification from gravitational lensing. And so use the Sun as a telescope, and if you move your detectors around that focal plane, you can, of course, sample different distant parts beyond the Sun that you're gravitationally lensing. It's tricky because the focal plane is a distributed thing. It's not just one point in space, and so you have to have a roaming set of detectors, and you have to gather the information and reconstruct what the focal plane looked like. So it's a computationally very challenging job, and the technology of setting up this experiment is challenging too, because it's very far from the Earth orbit, the place where you'd have to find this focal plane. So I think it's a very interesting project. There's some engineering designs behind it. It's probably 20 years off if it ever happens, and it will be pretty expensive NASA project. Maybe the private sector will get involved. So thanks very much for all your questions. Good variety today, and like I say, we'll make some arrangements for a couple of live sessions while I'm in Europe. So stay tuned for when those are. We don't know right now, so it'll be announced. And thanks to Matthew for facilitating.
Excellent. Thank you all very much for coming today. We appreciate it. I will put on the post-stream role. Again, thank you for your patience today as I was dealing with a little bit of technical challenges from a changed setup. And I will put on the post role so you can all chat for a few minutes if you'd like. And we will see you again in a couple of weeks. Take care, everyone.